It gives me insane, tremendous pleasure to introduce Marc Rosenbaum for a couple of reasons. But he's an MIT grad, and it completely changed my impression of MIT. So thank you. But more importantly, I met Marc and I met Betsy Pettit at the same event at the same time, and my relationships with both people have been rewarding and interesting. I mean, they're not the same.
Our first date just didn't go well.
Well, neither did mine. You're going to get in trouble for that.
Yeah,
right. Marc is crazy wonderful. He built ultra-efficient homes in the 70s. My God, you know, that was the time of like good music. He's a principal of Energysmiths, and he's going to talk to us about, believe it or not, monitoring using data to solve problems. And my brief comment is, if you can't measure it, I don't believe it. But if you do measure it, you might not know what to believe. So please, welcome Marc Rosenbaum.
That is accurate. Thank you. 25th, isn't this awesome? 25 years. And I want to say just to start how much I have appreciated being part of this community. And I want you to all think about how fortunate we are to work in this field, this small part of a very large field, where people really support each other and help each other learn and make incredible lifetime friendships. You know, so that's not common. If you talk to people about their work lives, we are super, super lucky. And I have learned so much from a bunch of people in this room. I mean, some of it's wrong, but so I just want you to think about that. And particularly, I want to invite the young people to really absorb that here. And also to understand essentially the lineage within which we work. The old guys like Joe, Terry Brennan, Bill Rose, and then the people that they tell us about, who was the earlier generation. It puts our work in context, right? So you know how we got to where we got to. So I want to make one disclaimer about this presentation, which is that I am not a professor. I do not work at government labs or private labs, and so I am a really sloppy measurer. Because my feeling is if you can get to 20% plus or minus, you probably can get the information you need to do something. So I'm always looking for actionable items out of what I'm measuring, right? And plus or minus 20% with buildings in many cases, not all, is plenty good to understand trends, understand what's going on. You know, over my career, I have checked probably hundreds of energy models and heating and cooling loads, which are off by factors of 2 or 3 or 4, right? So 20% on a building load is probably pretty good. We're not looking for perfection. As I move forward, if you have a question, something I wasn't clear about, or you think I'm just plain wrong, sing out. If it's something we should argue about over beer, I will defer it. All right. The AIA at all the other conferences I go to make people do things. So here's my mandatory AIA warning slide. I'm going to go on. How I got here. So you can't read this, which is true of most of the slides. I'm an engineer, not a graphic designer. If you could read this, you could see that my grandfather in 1921 was the 9th licensed electrician in Massachusetts. And as a small boy, like 10, 11, and I wasn't, you can imagine I was small, I worked with him in the summers. Newton, Massachusetts is where I grew up, where he grew up. We never worked in new construction. I never went on to a new construction job site. It was all old work. It was doing stuff or running stuff in old houses. So when you've got a 90-pound or whatever, 70-pound 10-year-old, who gets to string wires in knee walls and attics and crawl spaces? So I resolved that I would be the first one in my family. I am going to go to college. I'm not doing this shit. So you can see how that turned out. All right, so this is quoting another famous building scientist, Andy Shapiro, who always says, when we start something, why bother? What do you care about? He never answers that question, by the way. It's always so easy to ask the question. So I have a number of reasons why I measure stuff. To measure the performance of a building or a system, to solve a problem, to identify a problem that no one else has noticed yet. So I have monitored a lot of my buildings. And most of the people in our field are not going back and looking at how the buildings really perform. And so if there's stuff that I know that some of you don't know, it's because I measured it and looked. And then when I saw stuff that didn't make sense to me, I had to measure it more. Doesn't mean I always understand it, but sometimes you're looking at data and you see things that no one saw. This is an important one, and I have two great examples of this. Sometimes you know exactly what's going on, but you can't get people to believe you. So you take data, and you'll see it can be convincing. Sometimes you have monitoring that's already been done, and it can be used as inputs for a new design. Sometimes you have things that are happening, and you have no idea what causes them and what happens afterwards. And then you may just want to learn something. So curiosity is its own reward. And as Joe always says, stay curious, because that's how we learn new stuff. And some of you youngsters may not know Lawrence Barra, but you can observe a lot just by watching. Okay, types of monitoring that I use. Now, some of this is old-style stuff, because it's things that I don't necessarily, the more new, fancy stuff I don't understand. So sometimes it's long-term, and we leave it in place, and we're taking data over a long period of time. Sometimes we put monitoring equipment in for a short period of time to solve a problem, and sometimes we're just measuring a single data point to confirm how something is working. So these are some of my favorite tools. These are onset computer hobos, and the one on the left that has my initials on it is an old-style unit without an LCD display. It is a multi-channel. It takes temperature and relative humidity, and it's got two external channels for external sensors. The one on the upper one at the top is the new model. It's got a display, so it reads out what it's reading at the time, and it also has a lot more data storage, so you can leave it in place longer. And then I've got a couple of sensors. I've got a 50-amp current transformer to put on a sizable, something like maybe a big heat pump or something. And I've got an indoor-outdoor temperature sensor. And if you look at that temperature sensor, I'm not sure if you can see the tip. It's maybe 1/8 of an inch, maybe a little bigger. It's not very fast reacting. So when you're measuring temperature, you have to decide, do I need to know what the temperature is right now, or is this a longer term? It's good enough if it takes 5 minutes for it to equilibrate. These units require a laptop to set up. Onset has software that you use. The newer ones are Bluetooth, so you don't have to plug something in. And then if you spend more money, you get Wi-Fi, and you can do it over the net. When you look at the software that they give you, you're setting up I can't even read my own slide here. But you're setting up, it tells you the battery health, battery level, what sensors you're putting in, what channels. It's very important to know what channels, if you've got 4 temperature sensors, know which channels you're plugging them into. Don't ask me how I know about that. And then one of the cool things is deployment. I love that term. We used to say, "Where are you going today, Mark?" "I'm going out to deploy some hobos." Sounded good, didn't it? So you can set the logging interval. You know, so you might only need something once per hour, or you may want it to log much faster, much more frequently. This particular unit I sent off to a client who wanted to change his aging oil furnace to a heat pump. And one of the things I do when it's the winter time is I will, particularly if it's an oil furnace, I'll have the person put a current transformer on the oil pump and an outdoor sensor, and tell them to leave the thermostat at 70, don't mess with it for a couple of days, and just look at what percentage of an hour in a cold period is the furnace or boiler running, right? And it's a good way to get a sense of what the actual heat loss is of a building. One of my clients in Western Mass sent me back the logger after we did this, and I said, "Oh, that's interesting. It ran 100, it was like, 3 below 0. It ran 100% of the time." And so either his heat loss is high or he's got a really bad distribution system. What you discover when you do something like that is that most systems are grossly oversized, right? That's one of the consequences of this kind of measuring. I did this on, the first house I bought on Martha's Vineyard had a Buderus boiler. That's the blue ones, there's the blue ones and then there's the orange ones. I don't want to offend anybody here who might be selling these products. So I had a Buderus boiler with a remote water tank with a heat exchanger inside it as a zone. And I measured its efficiency in the summertime when it wasn't making heat. So you got a boiler that's got 8 gallons of water in it, and it has to, when the aquastat on the tank says, "I need heat," the boiler has to fire, bring itself up to temperature, start the pump, heat the tank. When the aquastat is satisfied, the pump stops, and the boiler's sitting there at 190. I was making hot water in that house at 11% efficiency in the summer. Digital multimeters, instantaneous measurements is what I'm using them for, but there are loggers, ones that log. This one does DC voltage as well as AC voltage, resistance, amps. One of my favorites is a good digital thermocouple. This is a 2-channel, and one of the things about this particular thermocouple is you can see how small it is. So it's very fast reacting. It equilibrates in air in a few seconds. So it's useful for a different type of measurement than those indoor-outdoor sensors on the hobos. There's a story about this unit. So this is for 120 volt loads, you plug this into an outlet and you plug something into it, and it gives you voltage and amps and watts, and you can get ones that log. When these came out, they were about 30 bucks, and I thought, this is awesome because I have a previous instrument that's quite a bit older that cost me $150. They weren't common. They weren't a consumer item. So I ordered 2 of these off of eBay and from the same vendor. And of course, they weren't shipped in the same package. So the first day one comes, and I'm excited because I'm a nerd, and I plug it in, and I plug something into it, and all it reads is 8888. So I thought, okay, maybe the outlet's screwed up or whatever. I put a different outlet. I plug different things in it. No matter what I got, it says 8888. So I contact the seller, and I tell him, and he says, send it back. I said, I'll wait for the next one to come. Next one comes the next day, same thing. I even read the directions. That's how desperate. Well, I managed, even though this is made in some obscure place in China, I managed to find the company that made these things. And I sent them an email describing carefully what my problem was. And I got very quickly a response that I very much appreciated. And it said, "Dear Mr. Rosenbaum, kindly remove the decal from the LCD display." So, Joe is like this big thing about, he went to MIT and everything like that. Like, doesn't guarantee much. Certainly, certainly doesn't guarantee very much intelligence. No, but you know what I noticed is that subsequent ones that I saw, like in the next year, had a little. It said remove decal. Yeah.
You made them better.
Yeah, it's like product testing.
Yeah.
God. Anyways, this is CO2 monitor, a Telair. I use these with hobo loggers. They have their own dedicated ones, but they're basically Telairs. These are self-calibrating. I never really trusted CO2 control because I worried about these things always drifting. But these are self-calibrating, and usually before I use one, I take it outside for a couple of days. And, if it doesn't read somewhere around 400, then there's something wrong with it, right? So, and again, this is a great example. I don't care if it's really 385 ppm and it reads 415. I'm looking for, is my ventilation system doing the right job in a classroom or in an office space or something like that? And plus or minus 50 parts per million of CO2 is not critical. This is a, I don't know, maybe about $200 radon monitor, and I think this is a great product. I had a very expensive traceable to NIST radon monitor for a while that I used in my house to do a bunch of testing. And I have two of these, and I tested them along with that one, and they're really pretty good. And again, we don't care whether it's 4.5 or 6. Is it 30 or is it 10? So I think these are about $200. They take hourly readings. They download by Bluetooth to your phone. And you have to make sure that you don't set an alarm, or it will be telling you all the time that you're over the limit. And then this is a whole system of monitoring, and I think you've heard a bunch of this from Coda and others over the years. Omnisense, where you can embed these sensors into building assemblies. This is just a great system. Web accessible, temperature, relative humidity, dew point, CO2. They have lots of different sensors. And then the last thing is circuit by circuit monitoring on your service panel. So this is my own house. This is a week's worth of data. I've got current transformers on about a dozen circuits at the house. And what you see here is the green humps are the solar system, the PVs making power. The pinkish red is house usage. And what's kind of interesting is the white at the bottom is how much of the PV energy is being used contemporaneously on site versus exported. And from my measurements in multiple buildings, the answer is if the building's net zero and it's got a fairly typical housing profile for usage, about a quarter of that energy is used contemporaneously, and the rest is exported and then re-imported. There's two big spikes that are 8 kilowatts. You want to guess what that is? It's a car, right? Yeah, I had like a $1,500 credit with Eversource, and they don't write you a check. So I realized I had to up my usage. And we got an electric car, and now I'm net zero, just like within like 1%. But unfortunately, that doesn't mean you're net zero cost. There's always there's a house percentage there. So soon I'm going to start paying an electric bill. All right, let's talk a little bit about calibration. Yes?
What system do you use for the circuit monitoring?
I used to use what was called SiteSage. It was called eMonitor first and then SiteSage, and now we're using eGauge. And that's mostly because I think the SiteSage folks really went to commercial, and they used to be super responsive with any kind of tech support, and they just kind of bagged taking care of residential clients, I think. So eGauge doesn't have as nice of an interface as the SiteSage, but they're very responsive, and I think that the technology is good. Thanks for asking that. Calibration. Can the instrument be calibrated to a known standard? You can see how much I care about that. This is more to the point. Can the sensors of the same type be calibrated at least to each other? So one winter, I wanted to monitor my ERV. So I'm using 4 different temperature sensors, 1 in each airstream. And the first thing I did is I zip tied them together and let them sit for a week and a half. And they were actually remarkably close. They were remarkably close. So that's my way of calibration in some cases. It's just that I don't have a bias that exists because I'm using 2 ostensibly identical sensors and I'm getting different answers. So here's my 2 radon measurements over about a week. And the maximum difference was 33%. And that happens right at the beginning at the lowest measurement, right? So that's going to be, well, it's 3 and 4. But over that period of time, the difference was 1.4%. So to me, the kind of thing I'm trying to do, good enough. And then there's this question, is each measurement critical or are you averaging results? Okay, accuracy versus precision. Accuracy is how close to the true value a measurement is. And precision is if you measure the same thing a bunch of times, how close together are those numbers? So you can have something that's very precise but not accurate. Does that make sense? Right? They could be 10% off the real value, but you get that repeatedly as the answer. And then I think the question you always are asking is, how accurate do the results need to be useful? Okay. If you've got a fast-acting temperature sensor, then to me you get the most accuracy by using the same sensor in 2 places. So here I am measuring the temperature rise across my little ducted heat pump, and I got a little hole, 16th-inch hole in the supply and the return, and I stick the thing in there, and then I move it, and then I move it back. I do that 3 or 4 times. I'm using the same sensor, so that number is probably pretty good. All right, so now I'm going to go to some cases, and I'm going to go back to that little heat pump. One morning it was 7 below on Martha's Vineyard. That, I know, my good friend Mike LeBeau is here, and he said, oh, and he's thinking, oh, springtime. Duluth is not an inhabitable by humans location. 7 below is cold. So I measured the temperature rise across the air handler at just under 40 degrees. I think that's amazing. Amazing. It was delivering 108, 110 degrees when it's 7 below outside. Old people who learned about heat pumps in the old days, this is a pretty amazing thing. The flow rate measured with a duct blaster was 368 CFM. The input power by the circuit monitoring system was a little over 2 kilowatts. So I can calculate what the heating power that was delivered to the house was, 4.64 kilowatts. So I don't know, 16,000 BTUs an hour, something like that. And then I can divide that power that was delivered by the power input, and I get a COP. So this little machine's making a COP of over 2 at 7 below 0. This is kind of magic, right? The Japanese, really focused on this, and they did something pretty cool. I was curious, so how much of this energy is going to the basement? So my house is a retrofit, so there's no insulation under the slab. There's 3 inches of polyiso on the walls. And the ducts are quite well insulated in the basement. They're pretty tight. I think this whole system is maybe 27 CFM 25 or something like that. They're pretty good. I did it, so it wasn't done by a professional. And I was curious, like how much ends up in the basement? So I decided a good surrogate measurement for that was I averaged the delta T across all the supply registers. And it's a 1,300 square foot house, so all the supply registers are 6. And the return, and it was about 35 degrees instead of 40 degrees. And so Mark's quick and sloppy calculation says that the temperature drop divided by the initial temperature differential is 11%. So I'm saying, oh, okay, so around 11% of that energy goes to the basement. Got lost somewhere, right? It's conducting to the basement. And one of the things about really efficient houses is for a house that's the same size, but it's very efficient, the ductwork is the same length in most cases. And it might be smaller, but the area is not shrinking nearly as fast as the flow rates. So this house, had a furnace in it when I bought it. It was 3,100 CFM 50. It's 140 now. And so I'm probably moving about a quarter of the air around this house that originally was being moved. Totally different duct system. So the losses are going to be bigger when you're moving smaller amounts of energy around. So you have to actually pay more attention to air tightness and insulation of a duct system in an efficient building. Now, each of these calculations come from a series of measurements, and each one has inaccuracy. So I'm giving you the COP to 2 decimal points. That is a total lie, right? But it's not 1 and it's not 3, and it looks pretty good, right? I mean, you could do a statistical analysis of blah, 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 and maybe the answer is 1.8 to 2.4. I don't know. But I kind of found out to my gut, this is a pretty good system. All right, here's one that I have no idea yet what's going on. So this is kind of hot off the presses. This is a little daycare center that South Mountain designed and built about 3 years ago. 9,600 square feet, 1 story. It's a really good building enclosure. These R values are true R values, calculated with bridging and stuff like that. For you blower door nerds, it's 0.04 CFM 75 per square foot of shell. Okay? Do people know what that means? I know some of you people know what it means. It's really freaking tight. Okay? It's got European tilt-turn windows. I mean, I can't speak with them because I think they're Slovakian, and but it's got 2 10-ton heat recovery, variable refrigerant flow, air-to-air heat pumps, and 18 indoor units, of which 17 are cassettes. One's a ducted air handler. It's got 7 ERVs totaling 2,400 CFM, and most of them are on demand control, CO2 demand control. The reason it's got so much ERV capacity is that ASHRAE 62 for daycare centers for kids 0 to 4 years old. The numbers are nuts, I think. Now, I'm not an ASHRAE person. What's that?
Odor control.
Yeah, like that's the idea that the kids are going to be stinky,
Same thing goes for nursing homes.
Says the same thing goes for nursing homes. So anyways, we've got the CO2 set point at 600 parts per million. That's pretty low, right? Yeah, right? The machines still don't run anywhere near capacity. And this is a longer story over beer, but I feel like I made a number of decisions that made the building systems more costly by designing, assuming that there would be times when these machines ran at peak. Okay, so here's a year's worth of energy use for that building. It's a pie chart. Pie are square. No, cornbreads are square. Pies are round. And this building has a site EUI of about 7.4 kilowatt hours per square foot per year, which is pretty good. In IP units, it's got a site EUI of 25. So it's not like the best building I ever did anywhere, but it's a pretty good building, right? Slightly over half of it is the heat pumps. The outdoor units are blue, and the indoor units are that little sliver of orange. So the heat pump EUI is 3.84. Now, I totally didn't expect that. It's the second VRF building with heat recovery where the heat pumps are using much more than I thought. So I did this building at Hampshire College, which is a certified Living Building Challenge building. It's bigger than this building. It's got the hyperheat VRF heat recovery systems, and again, it's using twice as much as I thought. And the building, again, is a really good building. So, we made the net zero because anytime you do an energy model, some things are going to be higher than you estimated and some things are going to be lower. But I don't like it when it's the heat pumps. So this is upsetting to me. And these systems were put in by a really good installer. The startup was witnessed by the distributor, who's very good. The system design was done with the Mitsubishi design software, which tells you how much refrigerant to add, and all the sort of normal stuff, I think, was done right. So I'm still wondering whether I made bad decisions about choosing machines or whatever, because you could do this with several different configurations of machine. You could do this building. I chose these two units because a single 20-ton unit has too much refrigerant for the refrigerant concentration limits, which I think, you're nodding your head, but I think a lot of people don't even know that exists. And then these machines are supposed to be able to turn down to 15%, which I thought was, so I built this little model of all the different ways I could configure these, and this looked like the best.
Mark, what's the heating design mode?
I'm going to get to that. Because the heating design load is pretty different whether the ERVs are running or not, right? Because even though they're maybe 75% efficient, it's a lot of load. Okay. Summer months are highest usage. And this is not what feels like a high cooling load building. I mean, the cooling load's higher than the heating load, for sure. But it doesn't feel like, I haven't seen that on other buildings that aren't much more highly glazed than this.
What's the red in the pie?
The one that's about a third of the total, that's sort of like plug loads and lighting and plug loads, which comes out to be about a third. It's 2.4 kilowatt hours per square foot per year, which is right on target, Andy, for I think this occupancy. It's kind of, I expect it to be 2 to 3. So other things were kind of predictable. One of these slices is duct heaters. I was so nervous about moving so much air into some of these classrooms, 450 CFM into the big classrooms, even off an ERV, that I have post-ERV supplied duct heaters that come on when the air is below 60. And it turns out that the controls were completely misset. So the first few months, this thing was using a bunch of duct heater energy that it didn't need to use at all. Okay, there's minute-by-minute data on a cold, cloudy day where there was no occupancy. So I combed through the data to find a day, I know the weekends have no occupancy. I confirmed no occupancy because all 7 ERVs together were using 79 watts. That's just the controls, right? That's just keeping them alive, sort of. And I knew it was cloudy because I'm looking through my own monitoring data at home. By the way, this kind of work doesn't get paid for. Like, who's supposed to pay for this? This is your education when you do this, right? And it's also because I know the small heat pumps I put in are mostly working really well. If these big VRF systems are not working, then we're selling them to people based on carbon reductions, and it's not going to be true. So, and even if some of them work or most of them work, I need to understand why some of them aren't working if this one isn't working, right? So this was the day in the whole winter, that whole 12 months actually, that my heat pump used the most energy. And I looked at my PV system and it made very little. So this was a really, for Martha's Vineyard, it was cold. It was 20. The building runs at around 70, 71.
Is this the heat pumps we're looking at?
These are the two heat pumps, the two 10-ton units. And you can see that one unit, the one on the upper left, is literally going on and off. Doesn't look like a 15% turn down to me. Now, the rated kilowatts, that scale is like 8. It's going up to around 8 or something. 9 kilowatts is the rated amount at 47, right? So it's going to draw more at cold temperatures, and that's in the engineering data book. But this thing is going on and off. And the other one looks kind of different. So I don't yet know what this all means, but this is data. This day, the building used 324 kilowatt hours, and the heat pumps used 276. So everything else was 48. And I could look at, the duct heaters were still using a little bit, God damn them. And, I could look at where that was going. All right, to get to Bruce's question. The building has a calculated heat loss at design temperature, Bruce, of around 100,000 BTUs an hour, about 30 kilowatts.
At what temperature?
5 probably is what I used. I think our ASHRAE design temperature is 8. But remember that ASHRAE design temperature for highly ventilated spaces and buildings is dangerous. Like where I used to live, ASHRAE design temperature, Lebanon, New Hampshire, -8. It can be 30 below. So if you've got a building that's bringing in 6,000 CFM in a commercial kitchen and a dining, you better cover what could happen in that. So I tended, for this building, I probably use 5, Bruce, 65-degree delta T.
Not 100,000. 15 kilowatts is like 53,000.
You can see why they had me talk instead of Bruce. Because Bruce...
That's a factor of 2.
Bruce has not, a factor of 2 I'm not usually comfortable with. But Bruce has not figured out that I just told him that the ERVs weren't running. So my calculation for this building at this time, this day, where there was no ventilation, is more like 50,000. Okay? No, that's a good question. Now, you're relying on my calculation of the heat loss here. So the first thing someone's going to say is, well, the building's heat loss is really a lot more. I don't think it's a lot more. That I saw all the insulation go in. We've got someone said, well, but what about, someone said to me yesterday, what about the heat loss to the ground? I said, I don't know. It's reasonably isolated. There's 6 inches of foam under there. I mean, yes, it's not a passive house. It doesn't have a foot of foam. That's only German passive houses that have to have a foot of foam. So my calculated load for this building over this 24-hour period, the power it needs is 15 kW, and the heat pumps are using 11.4, and so Mark's sloppy math is that the COP is 1.3. Now, if you go into Mitsubishi data manual and you look at this machine at these conditions, uncorrected, okay, so I want to use that word uncorrected, which means it hasn't been corrected for defrost, it hasn't been corrected for line length, although these line lengths are not particularly long. So there's some correction factors that knock 5%, whatever. But they're publishing almost twice that COP. So something's going on, and maybe next year I'll know.
Or did you disaggregate the numbers for the 2 different heat pumps?
Yes, and they're a little different, Gary, but they're not massively different. Like, I don't think that...
What was the question?
Sorry. Did I look at the 2 different heat pumps? And of that 11.4, one was 5 point something, and one was a little over 6 or something. The averages were similar, even though the signatures looked very different. So Mitsubishi's going to send someone down with their data analysis tool and plug it in, and that's the next step. Because again, I'm not getting paid. I'm doing the least amount of work to kick people in the butt to move along. Okay, case number 3. The case of the high hot water use energy. So this is a little dormitory in Deerfield, Mass. It's about 10,000 square feet, 4 faculty apartments, 10 doubles, dorm rooms, 28 occupants. You can see in the roof there, in the middle of the roof, there's a solar hot water system. It's a 240 square foot drain back. It's got a 360 square feet total of storage. And I not only have sub-metering on the building, but I also am measuring domestic hot water use in gallons. Now, if you're going to measure hot water machines and how much they use for energy, if you don't measure how much hot water got used, then that data is useless, right? So you can get, like a Badger water meter for under $100, and yes, it's not connected to the internet, but you can go and read the damn thing, right? So you always want to measure how much hot water is being used. So this looked like the domestic hot water usage was pretty much what I assumed, but it was using a lot more energy. So I put some hobo data loggers with current transformers on the solar array pump, the solar side of the system, and on the potable side of the system. I also threw some on the heating elements in the backup tank. And here's my answer. It's really cool. Nice sunny day. You can see that from around, the pumps come on around 9:30 and they run most of the day, putting in a lot of heat in those tanks. And then this red box is 8 p.m. to 8 a.m. So the pumps were running all night. The controller was faulty. And they don't get a lot of energy from the moon. Now, 2 things about that building before I go on to this one. 2 things about that building. First of all, I just told you that that daycare center was using almost 4 kilowatt hours per square foot per year for the heat pumps. This building is using 2. Older technology, the single-phase VRF, PUMI units, not hyperheat, less ventilation by far, but 24/7 ventilation, right? So the building's continually occupied. So, kind of similar building enclosures, although this building had what are called Marvin windows. The next one we built too had what are called Pella windows. So the heat pumps were using a lot less energy in this building than in my newer building with the fancier heat recovery units. So there's something going on, I think, with the heat recovery units. But I don't know what it is. All right, so identify and solve a problem. Case number 4. This is a small Eastern technical school. It's their business school. It's over 200,000 square foot building. It's over a 5-story underground parking garage. So it's got fans and lights and all that shit down there. We set some very stringent performance numbers for this building. And one of them was 1,000 square feet per ton. So I know some people here are engineers, and 1,000 square feet per ton, pretty good building for a big building. Got a commercial kitchen, got a bunch of assembly space, mostly offices and classrooms. And we actually hit that number. MIT is an amazing school for facilities, or they were when Walt Henry ran it, the facilities department. They have a special unit that does facilities management the first 18 months to get the building running right. And then they hand it over to the regular people. Essentially, they've got a year's worth of commissioning in real time. And they don't do any setbacks. They make sure people are happy, and then they start going after the energy. So, what's that?
Metering and verification for a year.
Yeah, really, but really it's more about, are people happy? Are we doing the job, right? Because the buildings are about people, they're not about, right? So,
What was the question? What was the question?
There wasn't really a question. He said it was a year's worth of measurement and verification. And I was just embellishing that about, it's really about, are people happy, which is a good criterion to use. That first close to 18 months, the peak load was literally 1,100 square feet per ton. And that was a day that was, higher than design day. So I think we totally did what we were aiming for on this building. This is getting chilled water from a central plant. So that number is pretty well understood in terms of what the load is. It's a pretty tight building. We had to import people from the heartland to do blower door testing. We noticed that the ones from Minnesota have no hair, and we think that it has something to do with climate, but we're not sure. So we have they handed me after like a year and a half data on peak and annual usage. And for instance, peak electrical use, I thought was a pretty decent number again. 1 3/4 watts per square foot for peak. Lighting seemed really good. Plug loads was very low. If you have this data, it gives you a nice club when you're doing the next building and the mechanical engineer wants to assume that the lighting is 4 watts per square foot and the plug loads are 20, and we'll get to that in a minute, by the way. This is an academic building and everybody's got computers. It's MIT. They probably all have 2. So I thought this number was pretty good, but here's the interesting thing. The average electrical load was 2/3 of the peak. And that just smelled wrong to me. It's too much, right? It's that percentage is too much. So they had sent me this data to look at, and I got back to Walt Henry, who's retired long since, but was the director of engineering there. And I said, something's running all the time there that we don't want running all the time. Well, big commercial kitchen there, 6,000 CFM hood, but it's got a Mellink system on it, which is variable speed. And the way those work is they have an electric eye that goes across the hood, and that electric eye senses opacity of smoke. And as the smoke there's more smoke, it ramps up the fans. Well, the hoods were running full speed 24/7. For like a year and a half. It turns out that if you put the fire suppression piping in the path of the electric eye, you don't get a lot of turn down. And Walt said that he sent this back to some of his hench people. I think they're hench people. Like, you've got henchmen and Coda was a henchman of Joe, right? They're minions, but they're like lower, right? Hench people. So he gave it to some hench people, and they came back saying that they thought this was 30%. Because you're running the fans, but you're running a bunch more cooling and heating, right? So this is what you can do if you look at data. Because the building overall is doing fine. Everybody's happy. It's low energy building. They did a building by this is a famous architect, but he's a nice guy. But MIT did a passel of buildings with famous architects. And people probably know the Stata Center. It doesn't have a vertical surface anywhere. This building has essentially the same programmatic usage, and it uses 37% the energy per square foot of Stata. Yeah.
After this was discovered, did they do another year of commissioning once the building was corrected to see what else existed?
I don't know. What happens at these institutions, which is really interesting, is that people leave and institutional memory is gone. And I had a meeting in 2016 on a new building. This building started in 2001. And I had a meeting on a new building, and they were discussing the mechanical approaches. And I said, we did a 70-page integrated systems study for Sloan that looked at systems and floor-to-floor heights and daylighting and structure, all these things together to see what the optimum was. And it really matters because, for instance, if you look at it all together, it's not the cheapest steel package because the steel package are more pieces that are shallower. But one of the things that we did, I insisted that they did all the major ventilation things as vertical, not horizontal. And the building is mostly hydronic, which 20 years ago was a big deal. It's not so much a big deal today, hydronic cooling. And this building ended up below the high-rise in the code, below the high-rise part of the code. The floor-to-floor heights were shrunk just enough. Now, I don't know how much money that saves. I don't know how to put a value on that, but that's real money, right? So it's very hard to really estimate how much you save by doing things right. Okay, demonstrate the cause of a problem to a skeptic. This is the hardest one. This is the case of the Moldy Theater. This is a 270-seat black box theater in coastal Massachusetts. It's a 3-year-old building. There's mold on the seats and mold on the stage curtain, and the RH is over 80% in the cooling season. And the facility staff have been working with the design engineer for like 2 years trying to solve this. And he's running around saying it's coming from the slab. And so I had the good fortune of having solved another mold problem in a new building by the same engineer and architect a couple of years before. I love these people. It's a great team. So I said to the facilities folks, send me along the drawings. So I look at the drawings, and what I see is they have a 10,000 CFM constant volume air handler with 4 stages of compressor. Now, if you're sizing a system for a building that's going to have 270 people in it, but most of the time it doesn't have 270 people, even if you didn't oversize the crap out of the system anyways because you're an engineer, it's not going to be at peak very often, right? The outdoor air was set at a maximum of 2850, which is reasonable, but a minimum of 540, and there's no energy recovery. So that's just outdoor air being dumped in the space. Now, you can look at these 2 facts, and you know that the way it's going to work is a constant volume air handler, and it's going to, most of the time, being run only 1 compressor because the load isn't there. So what temperature is the coil going to run at? It's going to be pretty warm, right? So what happens to dehumidification? Yeah, it goes to... What's that?
You're not squeezing any of the moisture out.
This is a technical term, but he says you're not squeezing any of the moisture out. It's exactly right. You got it. So, you know, I could have charged them 30 minutes. You know, they sent me the drawings. I looked at them. System will never work. Need to change it. Make some modifications. Do something. No way. Engineer, architects dig their heels in. So, I did a peak dehumidification load from the occupants and the ventilation air. It's 10 to 13 tons. I looked at the equipment submittal. The dehumidification rated capacity is 3.8 tons. For people here who are not, you know, technically, you know, bent, and I mean that word deliberately, 3.8 is a smaller number than 10 to 13. So we put in an OmniSense system, thanks to Lou Harriman, who helped me, held my hand during all this stuff, and we monitored a bunch of stuff, and then we made a really hard-to-read graph. And the important thing about this graph to start with is the yellow line here is RH. And the total vertical scale is 82 to 94. And the places with all the ziggy-zags are 8 to 5, 8 a.m. to 5 p.m. That's when the system is energized. Okay? And so you can see that the humidity bounces around, but again, between 82 and 92. And then when the thing turns off, it kind of just goes up. So And the peak temperature outdoors was hot. It was like 85, but it wasn't like, you know, horrible. Anyway, look at the table. It's telling me that the dew point of the outdoor air ranged from 67 to 76. And the dew point of the supply air off the system ranged from 59 to 71. Now, you are not going to do a lot of dehumidification with that dew point range discharging. Oh, and by the way, this is after the engineer had made some modifications. They closed down, they minimized the amount of outdoor air, the minimum. They closed down the minimum amount of outdoor air. So we had less outdoor air than we started. So I kind of blew this up, and this is the first 4 hours of that day. And we're starting off, and it's 72 degrees out. And here's the cool thing about this graph, is that on the two bottom ones, the blue is the mixed air return in front of the coil. So it's returning from the room and the little that's coming from outdoors. And then the gold one that's near the bottom is the discharge air off the unit. And they go back and forth because what's happening is the compressor runs, and you can see the temperature in the room, which is the red, goes down. And by the way, the room is freezing because that's part of the engineer's strategy. I'll just make it colder, right? So the room is freezing. And when the compressor runs, the discharge dew point is below the mixed return dew point. As soon as the compressor turns off, the supply dew point is higher than the mixed air return dew point. Why? It's re-evaporating the coil moisture. They didn't believe us. So they hired their own engineer who said,
data never sways the true believer.
Andy said, data never sways the true believer. So anyways, they hired their own engineer, and he said, yeah, the system will never work. But what was interesting is Lou and I said, you know, you probably need to reduce the amount of CFM on this air handler. And really what you need to do is, the simplest thing is put in a good-sized dehumidifier. Just put in a, because it isn't this massive load when there's no one there. What the engineer proposed, which is interesting, and I don't know if they did this, was that they reduced the blower to 5,000 CFM, which I'm on the edge with because that seems too little, and that they reconfigure the whole unit to have reheat, hot gas reheat after the coil. So that's another way to do it. I think it's more complicated. It was the manufacturer said it was going to be, I don't know, 40, 50,000 to do that change. We thought it would be a lot cheaper to throw a dehumidifier in there, and it might not use more energy than what they were talking about. So, you know, the dorm with the mold, because of, I won't go into the dumb design, but the mold in the dorm got fixed at a cost of over $200,000. But that was an academic institution, so they are nice, and the trustees are friends with the architect who wears a bow tie, and no one, the school paid for it. This job, the person who contacted me is the owner of a big construction management firm who happened to be the chair of their board. And we'd worked together on other projects, and he's a tough bastard. So I am really hoping that whatever they did got paid for by the architects and engineers insurance, not by the school. One last thing that talks a little bit about highly ventilated buildings and ASHRAE design conditions versus real life. By the way, I'm not dumping on ASHRAE. Those tables are super useful for us, but you have to apply them with judgment about what building you have. This is a highly ventilated space, right? So the red line at the bottom, the first red line, is 103 grains per pound. That's absolute humidity. And that's the humidity at the ASHRAE designed for cooling design condition for this location. The second red line is ASHRAE's design for dehumidification condition. And it's 124 grains per pound. You can see how often in 10 days the outdoor conditions exceeded the ASHRAE design for dehumidification, and indeed got up to about 147 grains per pound. That's the kind of thing that Andy Ask has to deal with, even in the winter, I'm sure. But for us people that live in habitable climates, okay. This is another demonstrate the cause of a problem to a skeptic. This is a house on Martha's Vineyard where the rich and powerful visit and the poor try to support themselves, taking care of them. Until about 10 or 15 years ago, Dukes County, which is Martha's Vineyard, was the poorest county in the state in terms of people who lived there. So this is an interesting house. This is probably a 1980s, early 1980s house. And actually, when you look at the house, the drawings, not the house, the architect was really trying to do the right thing, and he was pretty smart. And the builder talked them out of all the good energy efficiency features. It was so interesting to see the difference between the drawings and the, what was there in 3D. So we have this house that has a central kitchen, dining, living entry, and then 2 bedroom wings. And in section, I've never seen another house like this. The wings are on crawl spaces. The central section's on a basement. That's not that uncommon. But the fact that the slab is at the same level is kind of interesting. So they bumped the central section because the view got better if you were up another 4 feet. So the basement floor and the crawl space floor are the same level. And in the bottom, you're looking at the oil furnace, and the magenta lines are the supplies, and the blue lines are the returns. And they did this clever thing where they put the returns to the bedroom wings in the risers of the stairs, the little short stairs that go to the wings. Okay, are you with me? Now, this is an old oil furnace. It's single speed, constant volume. They've got zone dampers on the supplies. You know this is a bad idea, right? Yeah. Well, first of all, when we went to this house, so the company I worked for was going to do a bunch of renovations to this house. I went and looked at it. I told the owner, you need a new heating system. And he said, no, I don't need a heating system. And it turned out he was a professor. And he was an expert in sustainability. It turns out that's what he's known for. So I can't argue with him. I'm not a professor. As you've probably figured out already, right? And I don't have a pipe. The first thing you need to know, which is kind of an important piece of information, is in this slide you were looking at the entire return grill area in this building. 3 2¼ by 14 registers in the toe kicks in the kitchen, because they didn't put the returns in those risers to the wings. This is not going to turn out well, right? So there's the furnace, and the supplies are insulated, the returns are not. And there's one of those motor dampers. You can see barely this one over here. And then this thing here is called a relief damper. And so the idea is that when a motor damper closes, that air's got to go somewhere or the furnace will kick out on high limit. Right? It'll get too hot. You can see that someone has already said, This is causing a problem. I'm going to tape the relief damper. But, you know, tape has a finite lifetime. I mean, Martin Holliday tested it in his backyard, but he didn't test this particular one. So, deploy hobos is always the right answer, right? So we put temperature and RH loggers in the living space and the outdoors and the crawl space and the basement and blah, blah, blah. We actually put a current transformer on the oil burner to track the burner runtime, but it wasn't that critical for this. Here's the data. One lovely February day where it got to 2 above 0, which again, for Martha's Vineyard is cold. This is the basement temperature. The basement hit 100 degrees. The bedroom wing thermostats are never satisfied. So those dampers are always open. The main space, which has the biggest load, that motor damper is always closed. And its air is going to the basement, which creates what's known as a radiant floor. Oi. This convinced him he needed a new heating system. Anyways. All right, case number 7, determine the proper inputs for a design. So this is the case of the imaginary internal gains. This is a project that I've been working on with Andy Shapiro for, 2 years now. And it's a beautiful building, and it's CLT, and it's a lab. So they have an existing 22,000 square foot lab building. This is central New Hampshire with a planned and now almost finished 30,000 square foot addition. And we're working with an engineer that Andy and I have both worked with who's very good. I mean, he's a very good engineer. And he's got a load for the addition at 323 tons, you know, under 100 square feet per ton. And I look at it and I said, what? And it turns out most of it is internal gains. He's got, because they've got freezers and all kinds of machines. So I said to George, you know, George, they have an existing building where they do the same stuff. So why don't we get 15-minute data for that facility? So we got 15-minute demand data for the existing facility, and we looked at it carefully, and we had a peak draw in that facility of 323 kilowatts. The 323 is only a coincidence. Or 15 watts per square foot peak draw, all electricity. So when we pulled out things like chiller energy and all the expeller fans and stuff like that, we could see that the internal gains were pretty small. And so we combed over that data outside the cooling system, and it led to our engineer accepting without any real pushback that our internal gains probably likely peak between 5 and 7. And so the recalculated cooling load for this building was just under 100 tons. Now, I'm very expensive per hour. How much is 200 tons cooling? More is the right answer. And to go back to that MIT building for a second, Walt Henry, who was the director of engineering at MIT at the time, told me on another building that he argued and argued and argued with the engineer about the chillers and the cooling load, and he lost. And so there were 2 300-ton chillers. He padlocked the power box on the second chiller and told the facility staff, if you're running out of, if you're bouncing up against the cooling load, you come to me and we'll unlock that box. Never, right? And then the other story he told me was that one of the cluster, and I'm using the term without the last syllable, which is really the right, MIT did 4 buildings before we did that Sloan building with the world-famous people like Maki and Gary and Stephen Hall, worst building I have ever been in. Toured that building with the architects for Sloan, and Buzz Udell, who was the lead, said, this is an inhumane building. If you've ever seen it, it's got, each dorm room has 9 windows that are like this big and recessed 2 feet from the facade. So it's like portholes, and you kind of expect to see waves. And it's a horrible building, and I think he won the Pritzker, you know. So like what architects think are good buildings and what we think are good buildings, except for some of the architects who are here. So one of the buildings was the media lab. And again, the cooling load was really high, 10 watts per square foot for the internal gains. And Walt said to the engineers, you know, the media lab has a building now. Let's go see what their internal gains are. 1 watt per square foot, not 10. Okay, understand cause and effect. So I've been monitoring radon in my house for years. And in the basement, I get, on average, maybe 14, 15 picocuries per liter. And on the first floor, I get like 1/10 of that. It's a 1-story house above the basement. And I think that if you talk to people like Terry Brennan or other people who've done a lot of radon measuring, what you learn is their sort of guideline is that the first floor over a basement or crawl space will have a radon level about half of what the basement is. My experience is in really tight houses, that ratio is much bigger because there just isn't that much air moving up and through from the basement to my first floor. And I've measured this in other superinsulated houses. So I've never really worried about the level in my house, but I'm curious, like, so why does it vary so much? Because those 48-hour real estate tests that they do are totally bogus, because radon is like, it's like Pee Wee Herman's EKG. So I've done years of different measuring and trying to correlate. Like 1 year, this was so much work. I was measuring the delta P between inside in the basement and outdoors hourly and trying to correlate with radon. Nada. I've tried it with temperature, nada. And what I'm correlating with now is barometric pressure. And I don't know whether the low pressure events, which are usually storms, that the effect is because the ground's saturated and it's like putting a lid on the ground and it comes into my basement. I don't know what's really happening, but here's an interesting graph. So I've manipulated, these are the radon levels, and you can see these peaks. And then I've manipulated the barometric pressure to just mirror the radon. And you can see that the low barometric pressure is when the radon peaks. So that's the only thing I have found that correlates it, but I don't know whether it's directly barometric pressure or it's because the ground's wet. And then my last case is really an interesting one. I'm going to go back to that little daycare center. This is the case of the mystery CO2. So it's a lovely building, Ryan Bushy, architect. We have demand control ventilation with ERVs based, and there's one that's on a time clock because it's offices and stuff, but it's mostly demand control based on carbon dioxide. We've got the Mitsubishis, another story. We've got ducted dehumidifiers for separate humidity control. So on Martha's Vineyard, there's hundreds of hours a year where there's no cooling load, but there's high dew points. And I was paranoid about mold in a daycare center. The kids are on the floor. That's, you know, even when they're standing up, they're still on the floor, really. So I did the duct heaters, which don't really need to run, and I did these dehumidifiers. And I did this kooky thing. The ERVs are enabled from 5 in the morning till 10 at night. And then the dehumidifiers are enabled in the remaining hours, 10 at night to 5 a.m. So the idea is that I want to share the ductwork between these two different systems to not double up the ductwork. And because the ERVs go to multiple rooms, I don't have to have a whole other set of ducts. And I'm pretty convinced, and I, again, asked my friend Lou, that if I handle the average dew point in the evenings, I'm going to be okay. I'm not going to have a moldy building. So what happens here is that, let's see, do I say anything about this? Maybe I don't. So the way this works is when the ERVs shut down, the louvers close off to outdoors. They're motor dampers. But then on the warm side of the ERVs, motor dampers also. And the dehumidifiers, there's 3, are across the supply and return, supply and exhaust of the ERVs. And so that has a motor damper which is closed while the ERVs are running or enabled and opened. So basically, at night after 10 o'clock, the ERVs are out of the system because of these 2 motor dampers on the supply and exhaust, and the dehumidifier can use the supply and exhaust as a recirculation. Does that make sense? So I'm just dehumidifying at night and not doing that during the day. And again, because the ventilation system doesn't freaking run anywhere near its capacity, there's no mold issue, and the dehumidifiers hardly run. I would never do this again. However, I still wanted to understand, are we doing the right job with the ventilation? Is the CO2 under control? And I started watching the CO2 monitors, and I noticed that it was rising in the rooms, sometimes at night. So first I called the director and I said, how late are the cleaners there? You know, or like, oh, what are you guys doing? Are there parties that I haven't been invited to? So, you know, first I thought, well, maybe there's something going on in the mechanical attics. I don't know, it's still off-gassing off of some of the spray foam. I put a Tel-Air up there, and no, nothing's going on up there. So this is a couple of days worth of data. This is one ERV that feeds 2 rooms. So that's the 2 different colors. The green line is the set point at 600 parts per million, which is a pretty low set point for an occupied CO2. That's if the machines come on at all, ASHRAE. And I have cherry-picked the data to show you the night that the CO2 went to almost 1,400 parts per million from 600. And you can see that sharp drop-off at 5 a.m. when the ERVs are enabled again, and they come on and they suck the CO2 level down again. So I never looked for something like this, and I had no idea what was going on. Like I said, I checked out the mechanical attics, nothing going on. So what I decided to do was, there was one classroom that was not occupied yet because they didn't have a teacher for it. And it, fortunately, is the classroom that's on the ERV for all the offices. So it gets ventilation anyway. And I put the CO2 detector in there. But I also put a radon detector in there. So there's the CO2, and you can see at the very right-hand side there's a spike. One night it's 1,200, almost 1,200 ppm. And there's the radon on the same time period. Where does radon come from? Where does the CO2 come from? I think it comes from the ground. Don't these curves look pretty similar to you? So I think my source is the ground. Joe, 5 minutes? You know what? I'm going to be done a minute early. And that is the, I have reversed this now to really confuse you. That's the barometric pressure. So, but it's inverted. So the highest number is the lowest pressure. So again, I've got the same thing going on. The radon level is driven by the barometric pressure, or maybe rain, but the CO2 mirrors it completely, and I think the CO2 comes from the ground. And, you know, I don't know what's in there. Like, is there a bunch of decaying bodies?
Jimmy Hoffa. Jimmy Hoffa.
Jimmy, you know what? We're done, right? That's the answer.
We do have time for questions. This is called the stump the chump part.
I already stumped.
That's great, Mark. Can you, this is not a question, can you give me a quick commentary of your experience with the 210 VRF systems versus small split systems, like mini splits? Anything you can say about the comparison?
I feel like I've got a lot of, Andy's asking, what's the difference between these bigger systems, heat pumps, and the smaller ones? And I have very little data on the big ones, 2 buildings, but they both have been concerning.
Anything else?
Oh. Just a comment. These E-gauge systems are short money to spend to learn a lot about your building. And one of the good things is you can get any of your energy geeks can get into the data without having to get into the DDC system of the building, which of course makes the building operators happy that you're not messing around in there. And it's very short money for what you can learn.
Yeah, you never will get any data off a system that's built into the DDC. You will never get any useful data. It's a waste of time.
I don't know if this is on. It is. Just an experiment. Have you ever thought for the radon, when the barometric pressure is really low, you're seeing that spike, and you're wondering if it's the barometric pressure or the rain, have you ever just got out the sprinkler and just watered the lawn around the building to see if that would do it?
I don't know how many acres I would have to water to make that. That's a great suggestion, but I don't know the answer. Thank you.
So short-term rain spikes are a known phenomenon of radon. In other words, heavy rains will produce a spike, and this is known, and it's short-term.
So what is it? Is it that it's literally not coming out of the ground, so the concentration goes up?
The rain is a lid.
Yeah.
That's it. And it's worse in the winter. The ground freezes.
Yeah.
And you vent the ground.
Yeah. Yeah. But
So
what's interesting...
I don't see that, which is interesting in my house.
Yeah.
My radon levels, as average in the basement, Joe, are higher in the summer.
Just a quick comment. The spike is short term, so it seems to occur during the first, hours of a heavy rain. And even if the rain continues, the spike will go down. So I'm not really entirely sure why.
There's still some physics to be done here, which is always a good thing. I want to say a little bit more about what Andy said about the E-gauge. We went to a session at Nessie that was supposed to be reporting data from passive houses, a bunch of big passive houses, and they had no sub-metering on these buildings, they're $50 million buildings or more, and they could have spent $10,000 and actually have some data. It's just inexcusable.
Coffee, 30 minutes. Yay, Mark. Woo!